giant phase commences, the star begins to fuse helium into carbon and oxygen in its core, and hydrogen fusion continues in a shell around the core. This is a temporary reprieve. Eventually, the helium fuel also runs out, and the star isn't massive enough to ignite the fusion of heavier elements like carbon and oxygen. At this point, the star can no longer generate enough outward pressure to support itself against gravity. The outer now unbound, expelled into space, forming a beautiful and often spectacular planetary nebula. This isn't related to planets. The term arose because early telescopes made these glowing shells of gas look like planetary disks. What's left behind is the star's hot, dense core, a dwarf. This core, despite containing a substantial fraction of the star's original mass, typically 0.5 to 1.4 times the mass of the Sun, has shrunk to an incredibly small size, comparable to that of Earth. This remarkable compression leads to astonishing densities. A single teaspoon of white dwarf material would weigh several tons on Earth. Imagine fitting an entire star's worth of mass into a sphere only a few thousand kilometers across. It's this extreme density that gives white dwarfs their peculiar properties and makes them so scientifically valuable. Understanding how a white dwarf resists gravitational collapse lies in a quantum mechanical phenomenon known as electron degeneracy pressure. Unlike normal matter, where atoms are mostly empty and can be squeezed, the electrons within a white dwarf are packed so tightly that they obey the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state simultaneously. When electrons are forced into such close proximity, they generate a powerful outward pressure, independent of temperature, which is sufficient to counteract gravity and prevent further collapse. This is why white dwarfs are often described as being supported by the stuff of quantum mechanics. This degeneracy pressure is incredibly robust, but it has limits. If a stellar remnant exceeds a certain mass, known as the Chandrasekhar limit, approximately 1.4 solar masses, electron degeneracy pressure alone is insufficient to prevent further collapse. In such cases, the star's fate is far more dramatic, leading to either a neutron star. But for white dwarfs, this quantum pressure provides a stable, though slowly evolving, final state. When a white dwarf first forms, it's incredibly hot, radiating away residual thermal energy from its stellar past. However, without any ongoing nuclear fusion, a white dwarf slowly, inexorably, billions and even trillions. It gradually fades from a brilliant white to a dim red, and eventually, if the universe lasts long enough, it is theorized to become a completely cold, dark black dwarf. This latter stage is purely hypothetical at present, as the universe simply hasn't existed long enough for any white dwarf to cool down entirely. So, the coolest white dwarfs we observe today are still radiating some residual heat. White dwarfs are not merely cosmic relics, they play a crucial role in our understanding of the universe. They serve as standard candles in astronomy, objects with a known intrinsic brightness, which allows astronomers to measure vast cosmic distances. This is particularly true for type Ia, which occur when a white dwarf in a binary system accretes matter from a companion star, eventually exceeding the Chandrasekhar limit and undergoing a catastrophic thermonuclear explosion. These supernovae are so luminous and their brightness so predictable that they are used to determine the expansion rate of the universe and even to infer the existence of dark energy. Furthermore, white dwarfs are excellent laboratories for studying extreme physics. Their intense gravitational fields can cause light to be redshifted, a phenomenon predicted by Einstein's theory of general relativity. The study of their atmospheres allows astronomers to probe the composition of stellar cores that were once active. They can also host planetary systems, with recent discoveries showing debris disks around some white, suggesting that planets or their shattered remnants can survive the red giant phase and orbit these dense stars. Some even show evidence of polluted atmospheres, where heavier elements from devoured exoplanets or asteroids have settled, offering a unique window into the composition of planetary systems beyond our own. The ongoing cooling of white also provides a cosmic clock, helping scientists to estimate the ages of star clusters and even the age of the galactic disk. Yet, despite their apparent stability, white dwarfs are far from inert. Their extreme conditions can lead to spectacular cosmic events, particularly when they exist in binary pairs of stars orbiting each other. If a white dwarf has a close companion star, its immense gravity can start to pull matter, primarily hydrogen, from the companion's outer layers. This stolen material spirals down onto the white dwarf's incredibly hot, dense surface, forming an ever-growing layer. As more and more hydrogen accumulates, pressure and temperature at the bottom of this layer increase dramatically, eventually reaching a critical point where it triggers a runaway thermonuclear fusion reaction. This sudden ignition causes a brilliant, temporary brightening of the white dwarf, known as a nova. Unlike a supernova, which often destroys the star, a nova is a surface event. The white dwarf itself survives, shedding the fused material back into space, only to potentially repeat the process again and again over thousands or millions of years. These recurrent novae are powerful cosmic beacons, showcasing the dynamic interplay of gravity and nuclear fusion on a stellar corpse. Even more dramatically, if a white dwarf continuously accretes enough material from its companion to push its mass over the Chandrasekhar limit, that critical 1.4 solar masses, electron degeneracy pressure can no longer hold. The star undergoes a catastrophic, complete collapse, igniting its entire core in an uncontrolled runaway. The Type Ia supernova, one of the most powerful explosions in the universe, briefly outshining entire galaxies. These standard candles are crucial tools for astronomers, allowing them to measure vast cosmic distances and, most remarkably, to discover that the universe's expansion is accelerating, hinting at the mysterious force known as dark energy. The study of white dwarfs continues to push the boundaries of astrophysics. Beyond their roles in supernovae, they offer unique insights into the properties of matter at providing laboratories for testing theories of quantum mechanics and general relativity. Scientists are also exploring whether white dwarfs could host life. While the stars themselves are inhospitable, their long cooling times mean that any planet surviving their parent star's red giant phase could be warm enough for liquid water for billions of years, powered by the white dwarf's residual heat. The discovery of polluted white dwarfs, those with atmospheres contaminated by heavier elements, provides direct evidence that these can consume planetary material, offering clues about the composition of exoplanetary systems and how they evolve over cosmic timescales. Ultimately, white dwarfs are a testament to the diverse and often surprising ways in which stars end their lives. They are not merely faint embers of former glory but active participants in the cosmic ballet, continuously revealing new secrets about the universe's past, present, and even its distant future. Their quiet, cooling journey through the eons will, one day, culminate in the hypothetical black dwarf, a truly cold, dark, and utterly invisible stellar remnant, a cosmic tombstone awaiting the very end of time itself. So, while they may seem like the universe's ultimate quiet observers, white dwarfs are anything but static. Their extreme densities and powerful gravitational fields make them engines for some of the most violent and energetic events in the cosmos. Imagine a star the size of the Earth, yet weighing as much as our Sun. That's the kind of mind-boggling compression we're talking about. This density isn't just a curiosity, it's what dictates their very nature and their interactions with their surroundings. The study of white dwarfs isn't just about understanding stellar remnants, it's about pushing the boundaries of physics itself. They are cosmic laboratories where we can observe phenomena that are impossible to replicate on Earth. For instance, the gravitational redshift of light from a white dwarf provides direct observational evidence for Einstein's theory of general relativity. Light literally loses energy as it climbs out of the white dwarf's immense gravity well, shifting to redder wavelengths. This isn't just an abstract concept, it's a measurable effect that confirms our understanding of spacetime. Furthermore, the atmospheres of white dwarfs are like time capsules, preserving the chemical signatures of their former lives. By analyzing the elements present in their outer layers, astronomers can deduce the composition of the star's core that once fueled nuclear fusion. And sometimes, these atmospheres reveal something truly unexpected, the presence of heavy elements like iron, magnesium, and silicon that shouldn't be there. This pollution is compelling evidence that white dwarfs are actively consuming the remnants of their own planetary systems. It means that after the parent star swelled into a red giant and then shed its outer layers, any surviving planets or asteroids might have been gravitationally disrupted, fragmented, and then slowly spiraled into the white dwarf, leaving their chemical fingerprints on its surface. This gives us an unprecedented look into the final fate of exoplanetary systems, offering clues about how common rocky planets are and what their ultimate end might be. The saga of a white dwarf is one of quiet determination, a long, slow fade into cosmic obscurity. Yet, within this fading, there's incredible activity and revelation. They stand as enduring monuments to stellar lives, silently orbiting through the galaxy, each one a unique record of a star's fiery youth and its eventual, compressed serenity. And as our observational capabilities grow, we peel back the layers of these stellar corpses, finding that the universe's most dramatic stories often unfold in unexpected places. And what of the future of these cosmic remnants? While the universe hasn't yet existed long enough for any white dwarf to cool completely into a theoretical black dwarf, a state of absolute cold and darkness, a true stellar ghost, their slow, inexorable journey towards this ultimate chill continues. This gradual cooling makes white dwarfs incredibly valuable as cosmic chronometers. By precisely measuring their temperature and luminosity, astronomers can estimate the age of the stars they reside in, offering crucial insights into the formation and evolution of galaxies, including our own Milky Way. It's like finding a cosmic stopwatch, measuring away the eons. The sheer longevity of white dwarfs also raises fascinating query distant future of the universe. In the far-off epochs, long after all the brighter, more massive stars have faded, these dimming embers might be among the last visible objects in a vast, dark cosmos. They could potentially serve as the ultimate cosmic graveyards, silently bearing witness to the universe so old that all the hydrogen fuel for new stars has been exhausted, and even the red dwarfs, the smallest and longest-lived stars, have finally winked out. All that would be left are these cooling white dwarfs, neutron stars, and black holes, adrift in an ever-expanding, increasingly intricate dance in a binary system layer of complexity and wonder. While we've discussed novae and Type Ia supernovae, these systems also offer a unique opportunity to study gravitational waves. As two compact objects, like a white dwarf and a companion star, orbit each other, they ripple spacetime, sending out gravitational waves that future observatories might be able to detect with greater sensitivity. This could open an entirely new window into understanding these dense objects and the extreme environments they inhabit. Furthermore, the pollution of white dwarf atmospheres by devoured planetary material provides a unique archaeological record of exoplanetary systems. It's like sifting through the cosmic ashes to find the remnants of long-dead worlds. By analyzing the precise chemical fingerprints left on the white dwarf surface, whether it's the signature of rocky planets rich in silicon and iron, or water-rich bodies hinting at ancient oceans, scientists can reconstruct the composition of the planetary bodies that once orbited these stars. This offers invaluable data for understanding the diversity of planetary compositions across the galaxy, and perhaps, even the prevalence of water-bearing worlds beyond our solar system. In essence, the white dwarf, often perceived as a mere end state, is a vibrant and dynamic cosmic entity that continues to surprise and inform us. From acting as precise cosmic clocks and standard candles to revealing the destructive dance of stellar binaries and providing forensic evidence of vanished planets, these stellar corpses are anything but dead. They are profound reminders that even in death, stars find a legacy that continues to shape and illuminate our understanding of the vast, intricate tapestry of the universe. Their quiet existence is a testament to the enduring power of physics and the endless secrets held within the cosmos, waiting to be unveiled. As our technology advances, our ability to probe the secrets of white dwarfs only grows. New generations of telescopes, both ground-based and spaceborne, are constantly refining our understandings. Future missions like the Nancy Grace Roman Space Telescope and the Square Kilometre Array, SKA, promise to unlock even more mysteries, from precisely measuring the distances to Type Ia supernovae, further refining our understanding of dark energy, to detecting the faint whispers of gravitational waves emanating from binary white dwarf systems. The precise measurements of white dwarf temperatures and luminosities, refined by these advanced instruments, will allow us to chart their cooling curves with unprecedented accuracy. This, in turn, will give us an even more precise cosmic clock, potentially allowing us to date the oldest star populations in our galaxy with remarkable precision and contributing to a clearer picture of the Milky Way's early formation. Perhaps the most enigmatic aspect of the white dwarf saga is their hypothesized ultimate fate, the black dwarf. While no black dwarfs have ever been observed, because the universe simply isn't old enough for any white dwarf to have cooled down completely, they represent the theoretical endpoint of stellar evolution for sun-like stars. A black dwarf would be a truly cold, dark, and utterly invisible stellar corpse, a dense sphere of degenerate matter, radiating virtually no heat or light. Its existence would be a testament to tales involved in cosmic processes, a silent monument to a star that lived for billions upon billions of years before finally succumbing to the cold embrace of the universe. The very concept of a black dwarf pushes the limits of our imagination, forcing us to contemplate a universe far older and colder than anything we can currently observe. They are the ultimate cosmic tombstones, representing a universe where all the stellar fires have finally been extinguished, leaving behind only the cold ashes of what once was. Ultimately, white dwarfs are far more than just dead stars. They are crucial laboratories for understanding matter under extreme conditions, testing the very limits of quantum mechanics and general relativity. They are cosmic time capsules, preserving the chemical fingerprints of long-gone atoms and offering insights into the formation and evolution of exoplanets. They are stellar workhorses, providing the precision necessary for measuring the expansion of the universe and unraveling the mysteries of dark energy. From their fiery birth as main sequence stars to their dramatic transformation into red giants, and finally, their serene, long cooling as white dwarfs, these celestial objects embody the grand, ongoing cycle of the cosmos. Each white dwarf, quietly drifting through the vastness of space, holds within its incredibly dense core the accumulated history of a star to unlock deeper secrets about the universe itself. Even with all we've learned, the story of white dwarfs is far from complete. There are still many active areas of research that promise to reveal even more profound insights. One such area involves the study of magnetic white dwarfs, which possess incredibly strong magnetic fields, sometimes billions of times stronger than Earth's. These powerful fields can significantly influence how matter accretes onto the white dwarf, affecting the dynamics of binary systems and even altering the properties of their atmospheres. Understanding their origin and evolution is a key puzzle in stellar astrophysics. Perhaps one of the most exciting frontiers is the continued search for exoplanets orbiting white dwarfs. While the violent red giant phase would seem to sterilize any planet, evidence suggests that planets can indeed survive. Some studies indicate that Earth-sized planets could even form after the white dwarf's creation from the debris disk left behind. The discovery of transiting planets around white dwarfs, where a planet passes in front of the star and causes a dip in its light, would offer a truly unity to study the atmospheres of a survived such a dramatic stellar transformation. These observations could provide crucial planetary composition and atmospheric conditions under extreme radiation environments, giving us clues about the potential for life in such long-lived, albeit peculiar, systems. The ongoing dwarf atmospheres by heavier elements is also a vibrant field. Each new discovery of a metal-polluted white dwarf adds another piece to the cosmic puzzle, detailing the composition of rocky and icy bodies that once orbited these stars. This forensic astronomy helps us understand the diversity of planetary building blocks across the galaxy, shedding light on how common elements crucial for life, like carbon and oxygen, are incorporated into planetary systems. Beyond individual stars, white dwarfs play a subtle yet significant role in the larger cosmic tapestry. As old stars die and become white dwarfs, they lock up a significant amount of stellar mass, effectively removing it from the cycle of star formation. This contributes to the gradual chemical enrichment of the interstellar medium, as the planetary nebulae they shed return processed elements back into the galactic gas, providing the raw materials for future generations of stars and planets. They are silent, long-term contributors to the cosmic web, that vast, interconnected structure of galaxies and dark matter that defines the universe on the largest scales. In essence, white dwarfs are cosmic chameleons. They've transformed from fiery giants into dense, compact objects, yet their roles in the universe are incredibly diverse and impactful. They continue to be a fertile ground for discovery, pushing our understanding of extreme physics, stellar evolution, and even the ultimate planetary systems. Their quiet, enduring presence reminds us that even in astronomical death, there's a universe of profound activity waiting to be explored. As research into white dwarfs progresses, we're not just confirming existing theories, we're also stumbling upon new phenomena that challenge our current models. One intriguing area involves the study of ultramassive white dwarfs, those pushing the very upper limits of the Chandrasekhar limit. These rare objects are thought to be the result of the merger of two less massive white dwarfs, a cosmic collision that can lead to an object so dense and massive it barely avoids becoming a neutron star. Such mergers could also be a source of type Ia supernovae, offering an alternative to these powerful explosions that doesn't require a companion star. Another captivating aspect is the phenomenon of oscillating white dwarfs, also known as variable white dwarfs. These stars exhibit subtle, rhythmic pulsations in their brightness, much like seismic waves traveling through Earth. Studying these tiny variations, astronomers can perform astrometry, a technique analogous to seismology. By analyzing the oscillations, scientists can probe the internal structure of white dwarfs, revealing details about their composition, temperature gradients, and even their rotation rates, much like how geologists use seismic waves to understand Earth's interior. This allows for a unique, otherwise inaccessible, look into the heart of these incredibly dense objects. These pulsating white dwarfs are vital for refining our theoretical models of stellar evolution and the physics of degenerate matter. They act as natural tuning forks, providing precise data that helps us test our understanding of fundamental physical laws under conditions far beyond anything we can replicate in a laboratory. In a more speculative, yet fascinating, twist, white play a role in the ongoing hunt for dark matter. Some theories propose that certain types of dark matter particles could accumulate in the cores of white dwarfs, subtly affecting their cooling rates or internal structure. While still highly theoretical, precise observations of white dwarf potentially offer constraints on these dark matter models, making these stellar remnants unlikely, but valuable, partners in one of the biggest mysteries in modern physics. The sheer adaptability and informational richness of white dwarfs continue to amaze. From their role in understanding cosmic distances and the universe's expansion, to serving as forensic tools for lost planetary systems and offering insights into the most extreme states of matter, these stellar corpses are anything but inactive. Dynamic, evolving continue to reveal the universe's profound complexity, proving that even in stellar death, there is an enduring and captivating story to tell. Yet, even as we unlock these secrets, white dwarfs continue to hold profound implications for the ultimate fate of the universe. Their incredibly long cooling times mean that they will persist for eons, far outliving even the longest-lived red dwarf stars. This makes them central to theoretical discussions about the heat death of the universe, a scenario where the cosmos eventually reaches a state of maximum entropy, with all energy uniformly distributed and no further thermodynamic processes possible. In this unimaginably distant future, a universe old, dark black dwarfs, neutron stars, and black holes would be the final, silent act. The cosmic ballet of white dwarfs extends beyond individual stars. When two white dwarfs orbit each other in a binary system, their gravitational interaction causes them to slowly spiral inward, radiating energy in the form of gravitational waves. While these ripples in spacetime are incredibly faint, current and future observatories like LIGO and the proposed LISA, Laser Interferometer Space Antenna, are designed to detect them. The detection of gravitational waves from merging white dwarf binaries would not only offer powerful confirmation of Einstein's general relativity in extreme gravitational environments but also provide a new way to measure cosmic distances and potentially even understand the origins of some type Ia supernovae. The final moments of these mergers are thought to be violent, potentially leading to the formation of an even more massive white dwarf, a neutron star, or the aforementioned supernova. Furthermore, white dwarfs are increasingly being studied as potential cosmic lighthouses for medium. The dwarf, passing through the vast between stars, can be absorbed by various atoms and molecules in the gas and dust. By analyzing these absorption lines, astronomers can map the distribution and composition of the interstellar medium, providing crucial insights into the raw materials from which new stars and planets are formed. The ongoing research is that even seemingly dead objects in the cosmos harbor vibrant, active processes that continue to shape the universe and challenge our understanding of its fundamental laws. They are not merely endpoints but dynamic cosmic narrative, continually offering new puzzles to solve and deeper insights into the astonishing workings of the universe. And as our observational capabilities continue to advance, the humble white dwarf promises to remain at the forefront of astronomical discovery. The precision offered by space-based telescopes and the immense collecting power of next-generation ground observatories will allow us to scrutinize these stellar remnants with unprecedented detail. One of the most exciting prospects is the use of white dwarfs at the ages of the very oldest star populations in the universe. Because their cooling is so predictable, studying the coolest, faintest white dwarfs can provide a direct measure of the age of the galactic disk, and even potentially the globular clusters, which are some of the universe's most ancient structures. This acts as a cosmic stopwatch, allowing astronomers to rewind the clock and understand the conditions of the early universe and the first epochs of galaxy formation. It's like finding fossil records that tell us exactly when the first life emerged on Earth, but on a cosmic scale. Beyond the scientific breakthroughs, white dwarfs continue to capture the popular imagination. Their extreme density and ultimate fate evoke a sense of awe and wonder. They often feature in science fiction as remnants of ancient civilizations, or as sources of immense power, even though their real-life energy output is modest compared to active stars. This blend of scientific intrigue and speculative possibility, the stellar corpse remains a compelling object of study, both for seasoned researchers and for anyone gazing up at the night sky, pondering the ultimate destiny of stars. From their origins as the fiery hearts of stars, through their dramatic red giant phase, to their ultimate transformation into dense, cooling embers, white dwarfs are a testament to the diverse and complex life cycle of stars. They are not merely cosmic leftovers but active, informative participants in the ongoing story of the universe, continuously revealing new layers of understanding about physics, galactic evolution, and the very fabric of spacetime. Their quiet presence reminds us that even in astronomical death, there's an enduring and captivating narrative waiting to be explored. Beyond their individual mysteries, white dwarfs are increasingly becoming focal points in our understanding of the galactic ecosystem. The material they gently shed during the planetary nebula phase, rich in heavier elements forged in the star's core, returns to the interstellar medium. This enriches the gas and dust clouds, providing the building blocks for subsequent generations of stars, planets, and potentially, life. In a sense, every time a new star like our Sun forms, it carries within it the recycled remnants of countless stars before, including the material expelled by dying red giants that went on to become white dwarfs. This cyclical nature highlights the interconnectedness of all cosmic phenomena. Perhaps one of the most unexpected and exciting avenues of research is the connection between white dwarfs and the search for extraterrestrial life. While a white dwarf itself is a dying ember, its long, stable cooling phase could offer an extended period of habitability for any planets that survived the star's tumultuous red giant phase. If a planet is orbiting at the right distance, a habitable zone that shifts inward as the star cools, it could potentially maintain liquid water on its surface for billions of years longer than Earth will remain habitable around our Sun. This opens up the entry of second-generation life around stellar remnants, offering a vast, unexplored territory in astrobiology. The discovery of polluted white dwarfs, hinting at devoured exoplanets, further fuels this speculation, providing tangible evidence that planetary systems can exist around these stellar corpses. The study of white dwarfs is, in many ways, an art of stellar forensics. Each one is a crime scene, not of violence, but of immense cosmic change, preserving clues about a star's entire life and its dramatic demise. Meticulously analyzing their light, astronomers piece together the sequence of events, the original star, how long it lived on the main sequence, the elements it forged, and the chaotic events that led to its final, compact state. This forensic approach extends to their potential planetary systems, where the pollution acts as a chemical fingerprint of destroyed worlds, telling us what they were made of and how they met their end. In conclusion, the seemingly quiet existence belies their profound significance in the universe. They are not merely the end of a star's life but a vibrant new chapter in cosmic evolution. From providing fundamental insights into extreme physics and spacetime, to acting as cosmic clocks and distant lighthouses, and even offering tantalizing clues about life in the far future, white dwarfs continue to be a source of endless fascination and scientific discovery, pushing the boundaries of our knowledge with every new observation. As white dwarfs deepens, the focus shifts from simply cataloging these objects to unraveling their intricate roles in the grand cosmic narrative. We're moving beyond what they are to explore what they do and what they tell us about the universe's past, present, and far future. Even as they fade, white dwarfs continue to exert a powerful, though often unseen, influence. Their immense density creates a significant gravitational field that can subtly bend the light from more distant background stars and galaxies, a phenomenon known as gravitational lensing. While not as dramatic as the lensing caused by galaxy clusters or black holes, detecting these tiny distortions can offer a unique way to identify isolated white dwarfs that might otherwise be too faint to see directly. It's like finding invisible cosmic spectacles that subtly warp the view of the universe behind them, allowing us to weigh these elusive objects and refine our models of their mass distribution in the galaxy. Beyond their role in novae and type Ia supernovae, white dwarfs also bear witness to other cosmic catastrophes. The debris disks observed around some of them aren't just remnants of devoured planets, they can also be formed from the tidal disruption of asteroids or even strayed too close to the white dwarf's intense gravitational pull. Studying the composition and the way they feed material onto the white dwarf's surface, often glimpse into the destructive power of gravity in extreme environments. It's a cosmic demolition derby playing out in slow motion over millennia. In essence, white dwarfs are becoming the ultimate cosmic archaeologists. Each one is a dense archive of information, storing the history of a star from its birth to its quiet, drawn-out demise. By carefully analyzing their light, their pulsations, their magnetic fields, and the debris they accumulate, scientists can reconstruct the life story of billions of stars across the galaxy. This forensic approach allows us to not only understand individual stellar destinies but also to piece together the broader evolutionary history of star clusters, galaxies, and perhaps even the universe itself. From the most energetic supernovae to the quiet cooling over eons, white dwarfs are far more than just stellar. They are dynamic participants in the ongoing constantly of understanding about the universe's profound complexity and its astonishing, never-ending story. Beyond their individual mysteries, white dwarfs are increasingly becoming focal points in our understanding of the galactic material they gently shed during the planetary nebula phase, rich in heavier elements forged in the star's core, returns to the interstellar medium. This enriches the gas and dust clouds, providing the building blocks for subsequent generations of stars, planets, and potentially, life. In a sense, every time a new star like our Sun forms, it carries within it the recycled remnants of countless stars that came before, including the material expelled by dying red giants that went on to become white dwarfs. This cyclical nature highlights the interconnectedness of all cosmic phenomena. Perhaps one of the most unexpected and exciting avenues of research is the connection between white dwarfs and the search for extraterrestrial life. While a white dwarf itself is a dying ember, its long, stable cooling phase could offer an extended period of habitability for any planets that survived the star's tumultuous red giant phase. If a planet is orbiting at the right distance, a habitable zone that shifts inward as the star cools, it could potentially maintain liquid water on its surface for billions of years, much longer than Earth will remain habitable around our Sun. This opens up the intriguing possibility of second-generation life around stellar remnants, offering a vast, unexplored territory in astrobiology. The discovery of polluted white dwarf-devoured exoplanets further fuels this speculation, providing tangible evidence that planetary heat persists around these stellar corpses. The study of white dwarfs is, in many ways, an art of stellar forensics. Each one is a crime scene, not a violent cosmic change, preserving clues about a star's entire life and its dramatic demise. By meticulously analyzing their light, astronomers piece together the sequence of events, the original mass of the star, how long it lived on the main sequence, the elements it forged, and the chaotic events that led to its final, compact state. This forensic approach extends to their potential planetary systems, where the pollution acts as a chemical fingerprint of destroyed worlds, telling us what they were made of and how they met their end. In conclusion, the seemingly quiet existence of white dwarfs belies their profound significance in the universe. They are not merely the end of a star's life but a vibrant new chapter in cosmic evolution. From providing fundamental insights into extreme physics and spacetime, to acting as cosmic clocks and distant lighthouses, and even offering tantalizing clues about life in the far future, white dwarfs continue to be a source of endless fascination and scientific discovery, pushing the boundaries of our knowledge with every new observation. One of the most enduring on magnetic white dwarfs. Roughly 10 to 20% of all observed white dwarfs have strong magnetic fields, some billions of times more powerful than Earth's. The origin of these extreme fields remains a puzzle. Did the white dwarf inherit the magnetic field from its progenitor star, perhaps amplified during the star's collapse? Or are these fields generated anew during the white dwarf phase, perhaps eternal dynamo or a merger event? Unraveling this enigma is crucial not only for understanding white dwarfs themselves or gaining insights into stellar magnetic entire spectrum of star types. Beyond the visible and known, white dwarfs might even be silent sentinels hinting at the presence of the universe's most elusive components. Scientists are exploring whether some white dwarfs could have unseen companions, not just other planets, but potentially forms of dark matter. While speculative, precise measurements of white dwarf motions, cooling rates, or subtle gravitational effects could, in theory, reveal the gravitational tug of dark matter clumps or even primordial black holes orbiting them. Such discoveries would be revolutionary, turning these stellar remnants into unexpected probes for the invisible universe. Looking even further into the cosmic timeline, white dwarfs provide the most concrete observable link to the deep future of the universe. As the cosmos expands and cools, and as hydrogen fuel eventually runs out, star dwarfs will slowly burn out over trillions of years. The ultimate outcome will be a universe dominated by these stellar corpses, black holes, neutron stars, and the theoretical black dwarfs. These final, cold remnants will be the only enduring monuments to stars that once blazed brightly. Their study isn't just about what they are now, but what the universe will become in the unimaginably distant future, a silent, dark cosmos where the last whispers of stellar light have finally faded. In every facet, from their extreme physics to their role in cosmic evolution and their potential as probes for dark matter, white dwarfs continue to be a source of awe and scientific inquiry. They are a powerful reminder that even in stellar death, the universe offers endless frontiers for discovery, constantly challenging our perceptions and expanding our understanding of the cosmos. And the journey of discovery surrounding white dwarfs is far from over. As our technological capabilities continue to grow, we are pushing the observable, revealing ever more subtle and profound aspects of these fascinating stellar remnants. The most exciting advancements lies in our ability to perform incredibly precise measurements. Techniques like astrometry, which involves meticulously tracking the tiny shifts in a white dwarf's position against the background stars, allow us to detect the gravitational tug of unseen companions, even very low-mass planets or brown dwarfs that are too faint to observe directly. Weighing of the invisible provides crucial data on the prevalence of substellar objects orbiting white dwarfs, hinting at how common systems are around such evolved stars. It's a testament to the power of precision astronomy to reveal what's otherwise hidden. White dwarfs also play a vital, often understated, role as cosmic recycling plants. The phase, enriched with heavier elements like carbon and oxygen forged in the star's core, disperses into the interstellar medium. This enriched gas and dust become the raw ingredients for the next generation of stars, planets, and even the building blocks of life. Every atom of carbon in your body, for instance, was likely fused in the heart of a star that eventually became a white dwarf or a more massive star that exploded as a supernova. This continuous cycle of death and rebirth underscores the profound interconnectedness of all cosmic phenomena. While highly speculative, some theoretical physicists even ponder whether white dwarfs, with their extreme densities and unique quantum properties, could offer indirect clues to exotic physics beyond our current understanding, perhaps even hinting at dimensions or particles that interact with matter in ways we're only beginning to imagine. While this remains firmly in the realm of theory, it showcases how the study of these seemingly dead stars can inspire profound questions about the very nature of reality. In essence, White dwarfs continue to be a fertile ground for discovery, pushing the limits of our understanding across astrophysics, quantum mechanics, and even cosmology. They are silent, enduring testaments to the dynamic and ever-evolving nature of the universe, each one a compressed cosmic library waiting to reveal its next secret. In the grand cosmic ballet, where stars are born in dazzling nebulae and live out their lives fusing elements, the white dwarf stands as a profound testament to stellar evolution. Far from being mere cosmic ashes, these dense, Earth-sized remnants are vibrant laboratories of physics, active participants in galactic processes, and signs of the universe's history. From their incredibly compact nature, sustained by the enigmatic electron degeneracy pressure, to their role as standard candles for measuring cosmic distances and their dramatic involvement in novae and type Ia supernovae, white dwarfs continually push the boundaries of our understanding. They serve as cosmic clocks, allowing us to accurately date the oldest star populations. Their polluted atmospheres offer a unique archaeological record of devoured exoplanetary systems, hinting at the diverse fates of worlds beyond our own. Even in their gentle cooling over eons, they raise profound questions about the ultimate heat-death of the universe and the hypothetical black dwarfs that await in the unimaginably distant future. The ongoing study of magnetic white dwarfs, their subtle oscillations revealing internal structures, and the potential for their light to probe the interstellar medium ensures that these stellar corpses remain at the forefront of astronomical discovery. They are not static monuments to a bygone era but dynamic players in the ever-evolving cosmic narrative, constantly revealing new secrets about matter under extreme conditions, the life cycles of stars, and the grand, interconnected tapestry of the cosmos. Ultimately, the white dwarf reminds us that even in astronomical death, there is an enduring legacy, a wellspring of scientific inquiry, and a deep, captivating story waiting. NGC 6946, often called the Fireworks Galaxy, lies at the border between the constellations Cepheus and Cygnus, roughly 22 million light-years away. Though modest in size compared to grand spirals like Andromeda, it boasts an exceptional record of stellar cataclysms. Over the past century, it has produced at least 10 observed supernovae, far more than the Milky Way in the same time, earning it its explosive nickname. This high rate of supernova activity is not random. NGC 66 is a starburst galaxy, meaning it forms stars at a dramatically elevated pace. Its rich interstellar medium is packed with cold molecular clouds, which collapse under their own gravity to give birth to new suns. Many of these stars are massive and short-lived, burning through their nuclear fuel quickly before exploding as supernovae and seeding the galaxy with heavy elements. Its structure reveals tight spiral arms filled with pinkish hydrogen emission regions, H2 regions, glowing from the ultraviolet radiation of newborn stars. These regions are teeming with protostars and stellar nurseries, each one a pocket of cosmic creation. The galaxy's dust lanes, visible in infrared observation through the disk, obscuring and sculpting the view like shadows on a galactic canvas. In multi-wavelength image to X-rays, this appears as a chaotic yet harmonious symphony of gas flows, magnetic fields, and stellar winds. Embedded in the core lies a region of intense star formation, radiating not just invisible light but powerfully in the far infrared, suggesting vigorous heat from dust warmed by ultraviolet radiation. Unlike many grand design spires, this stellar structure lacks a sharply defined bulge or prominent bar. Instead, its central zone is soft, turbulent, and asymmetrical, possibly the result of past minor mergers or gravitational interactions with smaller companions now dissolved into its halo. Studies have revealed unusually magnetic fields that help shape the motion of gas and regulate stellar birth. These fields, mapped through polarized radio waves, thread through the spiral arms and are thought to be amplified by a cosmic dynamo effect, where the rotation and turbulence of the interstellar medium enhance weak seed fields into galactic-scale forces. Such magnetism can even affect the cosmic rays, adding a further layer of dynamism to this already vibrant environment. Despite all its dramatic activity, the fireworks galaxy remains relatively isolated, part of a small group within the M101 filament, a tenuous strand in the vast cosmic web. This seclusion may partly explain its high rate of star formation, as it has retained a rich supply of cold gas over billions. That reservoir continues to fuel stellar fireworks, solidifying its reputation as one of the most productive star factories in our galactic neighborhood. Each supernova in this system leaves behind more than just heavy elements and expanding shock waves. It marks a transformation of the interstellar environment. The resulting shock compresses nearby gas, potentially igniting the next wave of stellar birth. This feedback loop creates a rhythm, a heartbeat of death and rebirth across thousands of light-years. This galaxy also serves as a laboratory for understanding the connection between supernova rates and galactic environments. Its abundance of Type II supernovae, those born from the collapse of massive stars, offers valuable insight into the final stages of stellar evolution. Astronomers have used this stellar system to test models of core-collapse supernova progenitors, analyzing pre-explosion imagery of doomed stars and observing the fading afterglows. Its location near the plane of the Milky Way complicates certain observations due to intervening dust, but infrared and radio telescopes have managed to penetrate the obscuration. The chemical evolution unfolding within this galactic structure reflects the enrichment of its interstellar medium. Each new generation of stars forges heavier elements, carbon, oxygen, silicon, iron, within their cores, only to disperse them through explosive deaths. Spectroscopic studies of H2 regions along the spiral arms reveal metal abundance gradients, with higher concentrations toward the core. These gradients hint at gas inflows, stellar feedback, and radial mixing processes operating over cosmic timescales. The metal-rich inner zones suggest a prolonged history of star formation and recycling, while the more pristine outer arms likely point to recent accretion of primordial gas from intergalactic space. High-resolution radio observations have mapped out the galaxy's cold molecular reservoirs, primarily traced via carbon monoxide, CO, emissions. Giant molecular clouds, ranging from tens to hundreds of parsecs in size, act as stellar cradles. Within them, supersonic turbulent magnetic tension and localized gravitational collapse weave a dynamic tapestry that governs how efficiently stars form. Interferometric data from observatories result intricate structures inside these clouds, uncovering hierarchical clumps and filamentary strands at parsec scales. X-ray observatories, including Chandra, have revealed hot, diffuse large regions of the galactic disk, especially around recent supernova remnants. This plasma, reaching millions of kelvins, is produced by shock heating and contributes to the overall pressure balance of the interstellar medium. Together with ultraviolet and H-alpha imaging, these high-energy observations help quantify the energy feedback from massive stars, photoionization fronts, and explosions. Whether a given pocket of gas will cool and collapse into stars, or remain suspended as warm ionized material, depends on this delicate energy balance. Polarimetric observations have charted the orientation and strength of the large-scale magnetic field across this cosmic spiral. These magnetic structures not only influence cosmic ray transport but also shape the collapse of star-forming gas. Faraday rotation measures suggest coherent, ordered field across the disk, supporting the idea of an active galactic dynamo. The combination of spiral geometry and a rotation curve that steeply rises before flattening likely provides ideal conditions for maintaining this magnetic amplification over billions of years. The galaxy's own rotation curve has become a focal point in studies of dark matter. Observations in both optical and radio wavelengths between the motion of visible matter and the expected gravitational pull, pointing to an unseen mass component. Modeling the mass distribution indicates that the outer regions are dominated by dark matter halo, whose gravity governs not only rotational dynamics but also the retention of gas and metals throughout cosmic history. Although the exact shape of this halo remains uncertain, its gravitational influence is undeniable. Recent investigations into the interstellar turbulence of this system reveal a complex, multi-phase cold molecular clouds, warm atomic hydrogen, and hot ionized in dynamic interplay. Turbulent motions are driven by feedback from supernovae, radiation pressure, and differential rotation. Velocity power spectra indicate a cascade of energy from kiloparsec-wide flows to structures less than a parsec across, consistent with models of compressible magnetohydrodynamic turbulence. These turbulent patterns prevent collapse in some regions, while elsewhere, they foster the formation of dense filaments and clusters of stars. Out toward the galactic periphery, astronomers have detected subtle warps and asymmetries, likely remnants of tidal interactions or minor mergers. Though no major companion currently lingers nearby, telltale features in the neutral hydrogen distribution, such as extended gaseous plumes and skewed velocity fields, imply previous encounters with smaller satellites. Such interaction fresh gas inward, triggering waves of star formation. Simulations matching the observed hydrogen kinematics show that even low-mass intruders can imprint long-lived asymmetries and generate patterns, potential broken symmetry in this galaxy's arms. The star clusters within this spiral galaxy are of particular interest. Observations from the Hubble Space Telescope have resolved hundreds of compact stellar groups, many of them both massive and remarkably young, less than 10 million years old. These clusters function as miniature laboratories of galactic evolution, where internal dynamics are influenced by mass segregation, stellar winds, and the rapid life cycle of high-mass stars. Some of these formations may evolve into long-lived globular clusters, while others will disperse into the broader stellar population. Analyzing the age and mass distribution of such clusters, astronomers can reconstruct the recent star formation timeline, revealing peaks that likely correspond to global or localized bursts. There lies an enigmatic nucleus. While no definitive active galactic nucleus, age unconfirmed, hints of source suggest low-level or intermittent accretion. Infrared excesses and subtle radio emissions point toward the possibility of a hidden AGN, though its energy output falls far below that of typical Seyfert galaxies. The central region also hosts a nuclear starburst sustained by gas inflow driven by weak oval distortions in the galactic disk, an expression of slow, secular evolution. These gas flows may eventually nourish a dormant black hole, potentially reawakening central activity and illustrating the blurred boundaries of and active nuclei. On a grander scale, this galactic system occupies a node within a sparse filament of the cosmic web. Its proximity to the zone of avoidance, partially obscured by the Milky Way, has historically complicated its inclusion in large-scale structure maps. Nevertheless, recent surveys using radio and infrared observatories have begun to unveil its surroundings, a delicate network of diffuse gas and low-mass companion galaxies. These filamentary structures trace the hidden scaffolding of dark matter and baryons, offering a window into how galaxies grow in lower-density environments, far from the gravitational violence of crowded clusters. Stellar population synthesis models reveal a composite nature, ongoing star formation layered atop a much older stellar disk. The galaxy's distribution, covering ultraviolet to radio wavelengths, highlights both luminous blue stars and aging red giants. Integrated light measurements suggest a sustained star formation rate of around 4 to 5 solar masses per year, nearly 4 times that of the Milky Way, persist millions of years. This steady activity, fed by a stable gas supply and modulated by stellar feedback, provides a useful benchmark for the study of star formation in spiral galaxies operating in a regulated, main sequence mode. Despite its elevated activity, star formation in this system follows well-established laws. Observations of carbon monoxide and neutral hydrogen, combined with H-alpha and far-infrared emissions, demonstrate a strong correlation between cold gas density and star formation rate, consistent with the Kennicutt-Schmidt relation. This implies that even in dynamic environments, starbirth remains governed by predictable mechanisms. Within dense molecular clouds, gas cools via CO rotational transitions and fine structure atomic lines, allowing gravitational collapse to proceed. However, this process is delicately balanced by local factors, pressure, turbulence, magnetic fields, and feedback from newly formed stars that inject energy and momentum into their surroundings. One of the most intriguing aspects of this galaxy is the complex interaction between different phases of the interstellar medium. Spectroscopic and photometric analyses show the presence of multiple thermal dust and gas components. Cold molecular clouds at temperatures around 10 to 20 K dominate the millimeter regime, while warmer dust grains heated to 30 to 50 K emit strongly in the mid-infrared. Ultraviolet and soft X-ray observations trace highly ionized gas zones near OB associations and supernova remnants. These coexisting components underscore the ongoing exchange of energy between ISM phases, driven largely by supernova feedback and large-scale turbulence. This local spiral also plays an important role in the study of galaxy evolution across cosmic time. Many galaxies observed at redshifts around Z1 to 2 exhibit clumpy, turbulent disks and irregular morphologies, shaped by rapid star formation. Although more structured and mature, the galaxy in question shares several key traits: intense stellar nurseries, elevated gas fractions, and an abundance of massive clusters, making it an excellent nearby proxy for understanding the chaotic early epochs of galactic. Far-infrared observations from the Herschel and Spitzer space telescopes have yielded high-resolution maps of thermal dust emission. The dust-to-gas ratio here is relatively high, in systems' metallicity and ongoing star-forming activity. Spatial distributions of cold and warm dust align closely with the spiral arms, especially in regions rich in H2 zones and youthful clusters, where ultraviolet photons from hot stars heat surrounding grains. By modeling this radiation, astronomers can estimate dust mass, grain size distributions, and the strength of the interstellar radiation field across the disk. In addition to light and gas, cosmic rays play a crucial yet often invisible role in shaping the environment of this galaxy. Radio continuum surveys at around 1.4 GHz reveal diffuse synchrotron emission, produced by relativistic electrons spiraling along magnetic field lines, that maps the distribution of cosmic rays. These high-energy particles, originating from supernova remnants and stellar winds, permeate the galactic disk. They contribute to the overall pressure balance of the interstellar medium and influence both the ionization state and chemistry of dense molecular clouds. Suggests that the transport of cosmic rays is anisotropic, spiral structure and magnetic field lines, further evidence of the intricate coupling between energetic feedback and galactic morphology. The dynamics of the spiral arms themselves have also become a subject of focused investigation. Unlike grand design spirals with continuous, symmetric arms shaped by density wave theory, this stellar system exhibits a more fragmented, flocculent structure. Such morphology is likely maintained through rotational instabilities and swing amplification. Rather than static features, the arms appear to be evolving patterns, generated and dissipated through internal processes like gravitational collapse, shear flows, and stellar feedback. Numerical simulations of self-gravitating disks that replicate the patchy appearance of this galaxy occlusions, indicating that spiral arms can form and dissolve on timescales of approximately 100 million years, consistent with the diversity of ages seen among young clusters. Beyond the main disk, there is compelling evidence for ongoing accretion of gas from the surrounding cosmos. Deep HI mapping has detected low-density streams and filaments of hydrogen gas extending far beyond the visible stellar component, possibly the vestiges of ancient infall or minor mergers. These structures may act as slow, steady feeders of cold gas to the inner regions, sustaining star formation through so-called accretion. This mechanism is increasingly recognized as a key factor in the long-term evolution of isolated galaxies. The presence of faint, low-surface brightness features in the galaxy's outskirts hints at a more complex history than its relatively quiet appearance suggests. Stellar streams and warped HI layers may be the remnants of disrupted dwarf satellites or diffuse gas clouds captured by the gravitational potential well. Although such features are often obscured at optical wavelengths due to foreground extinction from the Milky Way, they are becoming more accessible through deep imaging campaigns and advanced radio surveys. Their chemical composition, motion, and alignment with the surrounding gas envelope point toward an ongoing sequence of minor mergers, supporting hierarchical models of galaxy formation. This spiral galaxy also provides valuable data for probing the distribution and nature of dark matter in disk galaxies. Its rotation curve, derived from precise velocity measurements in both neutral hydrogen and carbon monoxide, exhibits the familiar discrepancy between visible mass and observed rotational dynamics. The outer regions are dominated by a dark matter halo, whose gravity not only shapes the galaxy's rotation but also influences its capacity to retain gas. Attempts to fit various halo model Barrow-Frank-White profile or pseudo-isothermal distributions offer insight into the long-standing cusp core debate. Notably, the inner portion of the rotation curve appears to favor a cored dark matter, perhaps shaped by energetic stellar feedback that has softened the central density over time. Adding further complexity, the large-scale magnetic arc of this galaxy reveals coherent spirals not always align with the luminous arms. These so-called magnetic arms, identified through radiopolarization, span the interarm regions and appear stable over tens to hundreds of millions of years. Their structure is likely maintained by a mean field dynamo process, where the interplay between differential rotation and turbulence within the disk amplifies and organizes the magnetic field. These fields, in turn, regulate gas dynamics by guiding flows, resisting fragmentation, and applying pressure that can counterbalance gravitational collapse, thereby shaping when and where stars can form. The galactic center, though lacking a classical active nucleus, may nonetheless harbor a low-mass black hole nestled within a dense nuclear star cluster. Nearoscopic surveys have identified central peaks in volition, possibly indicative of a dynamically hot stellar population or the gravitational pull of a compact object. Due to dust obscuration and the absence of broadline features, estimating the black hole's mass is challenging. However, dynamical modeling places its upper limit at a few million solar masses. If confirmed, such a central black hole would occupy the lower end of the black hole mass-bulge mass relation, insight into black hole formation in late-type spiral galaxies. The intricate interplay of components in this system, stars, gas, dust, magnetic fields, and cosmic rays, illustrates the complexity of galactic ecosystems. Each constituent shapes and is shaped by the others. Stars enrich the interstellar medium, magnetic fields direct the flow of gas, dark matter governs large mix, and supernovae inject energy that regulates temperature, structure, and further star formation. Feedback loops within the disk are both limiting and generative, maintaining a high but stable rate of stellar birth while preventing rapid depletion of gas supplies. This galaxy also acts as a cosmic observatory, offering astronomers the full stellar life cycle. Its record-breaking number of supernovae, such as SN 2004 ET and SN 2017E, provides exceptional case studies of massive star death, from pre-explosion imaging to fading remnants. These events refine models of progenitor structure, nucleosynthesis yields, and the physics of supernova remnants. Intriguingly, some massive stars in this galaxy have simply vanished without producing a visible supernova, raising the possibility of explosions leading directly to black hole formation. One particularly notable case is that of N6946, BH1, a luminous red supergiant initially estimated at 25 solar masses, which dimmed and disappeared from optical view. The absence of an accompanying bright explosion, coupled with infrared emission, quiet gravitational collapse, possibly forming a black hole through fallback accretion. If verified, such events could represent a significant, undercounted population of stellar deaths, bypassing the traditional supernova route. This challenges existing models of core collapse, especially in regard to the influence of rotation, magnetic fields, and neutrino physics. The chemical composition of the interstellar medium offers another window into the gas. Spectroscopic mapping of H2 regions reveals clear radial gradients in elements like oxygen, nitrogen, and sulfur, typically decreasing with distance from the center. However, deviations from this trend, such as localized metallicity plateaus or sudden drops, may indicate recent infall of metal-poor gas, incomplete mixing, or spatial variations in star formation history. These chemical signatures allow astronomers to trace feedback-driven fountain flows, episodic gas accretion, or the radial migration of stars across the disk. Radial migration, in particular, plays a key role in shaping the distribution of stellar populations over time. Caused by interactions with transient spiral arms or weak bar-like distortions, stars can move significantly inward or outward while preserving near-circular orbits. This migration blurs the classical age, metallicity relationships and complicates attempts to reconstruct galactic history. Also explains how the outer disk can contain old stars formed in the inner regions. Such redistribution contributes to the development of extended ultraviolet disks and thick stellar components. In terms of triggering star formation, this spiral galaxy exhibits a variety of mechanisms. In addition to large-scale instabilities and spiral arm compression, there is evidence for self-propagating star formation. Observations reveal sequences of star-forming regions aligned along expanding shells, likely caused by pressure waves from earlier generations of stars. These waves compress nearby gas, initiating new bursts of star formation in a can. The resulting stellar complexes and clouds exhibit hierarchical, fractal-like structures. These patterns are supported by scaling relations between cloud size and velocity dispersion, consistent with turbulent cascade models of the interstellar medium. The cold dust component, traced by submillimeter observations from SCUBA and Herschel Spire, also reveals temperature and opacity variations across the disk. These properties are sensitive to grain size distributions, coagulation processes, and the local radiation field intensity. Dust grains play a critical role in shielding molecular gas, catalyzing the formation of H2 on their surfaces, and regulating the of star-forming regions. Variations in the dust-to-gas ratio across the disk of NGC 6946 are tied to its metallicity gradient, with lower dust content in the outskirts and higher content in the center. Radiative transfer models applied to the full spectral energy distribution, SED, help disentangle these effects and reconstruct the three-dimensional dust structure. On galactic scales, NGC 6946 exhibits signs of secular evolution, slow, internal processes that reshape its structure over billions of years. The lack of a strong central bar, but the presence of weak oval distortions and an asymmetric stellar distribution, suggest that internal distributing angular momentum. This, in turn, channels gas inward, sustaining the central starburst and potentially building a pseudobulge, a structure formed not by violent mergers, but by steady inward flow of disk material. Observations of stellar kinematics and photometric decomposition support the presence of such a component, with intermediate-scale enhanced alpha element abundances indicating rapid past enrichment. NGC 6946, then, stands as a vibrant, evolving ecosystem, an archetype of a gas-rich spiral undergoing sustained star formation and self-regulation. Its value to astrophysics lies not just in its photogenic appearance or prolific supernova rate, but in the way it encapsulates a diverse range of physical processes, from turbulence and magnetism to feedback and secular dynamics. It bridges the gap between local, well-resolved systems and distant, unresolved galaxies observed in the early universe, providing the empirical grounding necessary for testing and refining cosmological models of galaxy formation and evolution. In recent years, integral field spectroscopy, IFS, has become a transformative tool for studying galaxies like NGC 6946, offering spatially resolved maps of kinematic and chemical properties across the disk. Instruments such as MUSE, Multi-Unit Spectroscopic Explorer, and KCWI, Keck Cosmic Web Imager, enable astronomers to construct full 3D data cubes, capturing spectra at each pixel and revealing the internal motions of stars and gas in exquisite detail. For NGC 6946, such observations have shown that the velocity dispersion of ionized gas increases in the inner regions, likely due to turbulence from stellar feedback and central mass concentration. Meanwhile, stellar motions reveal a dynamically colder thin disk and a thicker, older population with higher vertical velocity dispersion, indicating layered components built up over time. Molecular gas kinematics observatories like ALMA and NOMA show that gas in star-forming regions often exhibits signs of non-circular motion, such as inflows, streaming along spiral arms, or localized outflows. These motions, when compared with gravitational potential models, suggest that the gas does not merely orbit passively but is dynamically active, flowing along pressure and gravitational gradients shaped by feedback, spiral perturbations, and possibly passings. These complex flows help drive gas toward central where it feeds nuclear star formation and potentially builds mass concentrations. Furthermore, NGC 6946 exhibits localized large cavities in the interstellar medium blown by clusters of massive stars. These bubbles, several hundred parsecs in diameter, are observable in H-alpha and X-ray maps, where they appear as shell-like structures surrounding diffuse hot gas. Some of these superbubbles coincide with past supernova remnants and are thought to have expanded due to overlapping shock fronts from multiple explosions. These structures can puncture the galactic disk, driving hot gas into the halo and forming galactic fountains, where enriched material is expelled from the plane and later cools and falls back, helping to mix the interstellar medium and redistribute metals over large scales. NGC 6946's extended HI disk, mapped with single-dish and interferometric arrays, shows that neutral hydrogen stretches well beyond the optical disk, up to more than 50 kpc in diameter. This vast, low-density component rotates more slowly and contains several asymmetries and warps, suggesting ongoing interaction with the surrounding intergalactic medium. Such extended HI structures are key indicators of external gas accretion, and their kinematics can trace the shape and orientation of the dark matter halo far beyond what stellar motions reveal. The flattening and stability of the HI disk over such scales also provide constraints on the total mass distribution and the potential triaxiality of the dark matter halo. Studies of resolved stellar populations in this galaxy, using ultraviolet and near-infrared imaging from the Hubble Space Telescope, have revealed age gradients and color diagrams indicative of continuous star formation spanning several gigayears. Its disk is home to a diverse stellar population, ranging from young, luminous blue stars in clusters to evolved red giants and asymptotic giant branch stars. This range of ages and compositions enables astronomers to reconstruct the galaxy's star formation history at fine spatial scales, revealing patterns of episodic bursts, intervening quiet periods, and radial stellar migration. In some peripheral regions, the presence of unexpectedly young stars suggests rejuvenation events, likely triggered by infalling gas or the outward extension of spiral arms into previously quiescent zones. On a broader cosmological stage, this system's position near the zone of avoidance, where the dense plane of the Milky Way obscures extragalactic views, makes it a key anchor for tracing the structure of the local universe. Velocity measurements and HI distribution studies confirm that it belongs to a sparse filamentary network connected to the M101 group. These filaments are not simply visual alignments but dynamically evolving structures molded by the gravitational scaffolding of the cosmic web. Investigating galaxies embedded in such filaments helps clarify how environmental factors, like gas accretion, merger frequency, and angular momentum acquisition, shape galactic evolution across cosmic time. This stellar system also plays a pivotal role in advancing theories of feedback-regulated star formation, a central element in galaxy formation models. The interplay between energy injection from young stars, via radiation, stellar winds, and supernovae, and the cooling and condensation of gas determines whether a galaxy continues to form stars or becomes quenched. In this case, star formation proceeds at a high yet self-regulated pace, suggesting a quasi-equilibrium state where feedback maintains sufficient turbulence and pressure to prevent catastrophic collapse while still allowing steady stellar production. Such a balance aligns well with predictions from cosmological simulations like EAGLE and Illustris TNG, which aim to reproduce the diversity of galaxy types through detailed modeling of baryonic physics. Ultimately, this galaxy is far more than a supernova hotspot or a visually captivating spiral. It serves as a richly structured, chemically evolving, magnetically ordered, and energetically self-regulating galactic ecosystem. It bridges the scales between stellar physics and the cosmic web, offering a unique window into how local processes interweave with the broader narrative of the universe. Through it, one can trace the mechanics, the cycles, and even the poetry of cosmic evolution. The galaxy's prominence as a star-forming engine is also underscored by its intense infrared luminosity. Observations from space telescopes such as Spitzer and Herschel have mapped the far-infrared glow from dust grains heated by ultraviolet and optical radiation. This places the galaxy near the threshold of the luminous infrared galaxy, LIRG, category, an impressive feat given its moderate mass and lack of major companions. The spectral energy distribution, SED, reveals multiple dust temperature components, with cooler dust in the outskirts and warmer regions concentrated in compact starburst zone. These thermal signatures allow for detailed modeling of dust grain composition, such as silicates and carbonaceous species, and their size distributions, which are shaped by processes like sputtering, coagulation, and photodestruction. On the molecular scale, high-resolution measurements of rare CO isotopologues like superscript 1 superscript 3 CO and C superscript 10 provide insight into the temperature and density structure within giant molecular clouds. These lines penetrate deeper into dense regions than standard CO transitions and help disentangle radiative transfer effects. The observations reveal that many clouds are clumpy, filamentary, and internally structured, with compact dense cores embedded in diffuse envelopes. This supports the idea that star formation follows a hierarchical, self-similar pattern. Shock tracers such as density tracers like HCN further illuminate the conditions required for massive cluster formation within these clouds. The galactic magnetic field subtly shapes many of these processes. Synchrotron emission maps from polarized radio data show that both ordered and turbulent magnetic field components are present. The ordered fields often align with spiral structures and persist even between arms, while the turbulent components correlate strongly with sites of active star formation and supernova feedback. The coherence of the regular field across kiloparsec scales points to an active large-scale alpha-omega dynamo, maintained by differential rotation and mirror asymmetric turbulence. These magnetic structures influence angular momentum transfer, guide gas flows, and even affect the fragmentation of collapsing clouds, potentially shaping the initial mass function, IMF, of new stars. In the time domain frontier, this galaxy has proven indispensable. Its high rate of core collapse supernovae provides a unique laboratory for comparing light curves, explosion mechanisms, and progenitor environments under consistent galactic conditions. Events like SN 2004 ET and SN 2017 E have been monitored in detail across the electromagnetic spectrum, offering valuable data for modeling shock physics, dust formation, and energy transport. Some of these supernovae have even produced light echoes, reflections of their light off interstellar dust, which enable three-dimensional reconstructions of the surrounding medium. These echoes reveal not only the nature of the explosions but also the small-scale structure and composition of the interstellar environment itself. Meanwhile, theoretical models continue to advance in parallel with observational insights. State-of-the-art hydrodynamical simulations, now incorporating feedback from massive stars, cosmic ray pressure, magnetic field dynamics, and realistic cooling functions, are capable of reproducing many of this galaxy's key features, from its patchy, flocculent spiral arms to its chemical gradients and regulated star formation activity. These results support the view that systems like this one represent a point of dynamic equilibrium, where energy feedback ensures structural stability, accretion maintains star-forming material, and internal processes build complexity without the need for major external perturbations. Beyond its own borders, this nearby spiral acts as a Rosetta Stone for interpreting galaxies in the distant universe. The clumpy, gas-rich disks seen at redshifts around Z1 to 2 often resemble scaled-up versions of this system. Its internal regulation, feedback cycles, and multi-phase interstellar medium provide a blueprint for interpreting less resolved galaxies in the early cosmos. In this sense, the so-called fireworks galaxy forms a bridge between the local universe and the formative epochs of galactic assembly. Its scientific legacy is thus multifaceted. It is a prolific supernova laboratory, a magnetically structured dynamo, a chemically complex feedback system, and a living fossil of secular galactic evolution. Every aspect, from its turbulent disk and star-forming rings to its coherent magnetic arms and diffuse halo, contributes to our understanding of how galaxies evolve, recycle, and interact with the cosmic environment. The photons that reach Earth after traveling over 22 million years carry not just images, but the imprints of stellar birth, death, and renewal. To observe this galaxy is to witness a chapter in the ongoing chronicle of cosmic evolution, written in light, gas, and gravity. Among the most revealing aspects of this narrative is the role of chemical feedback. Each stellar generation, particularly massive stars, contributes to the galactic ecosystem by returning the byproducts of nucleosynthesis to the interstellar medium. Elements such as oxygen, magnesium, and iron, forged in stellar cores and expelled in supernovae, enrich the surrounding gas, seeding future star formation. Thanks to the unusually high frequency of stellar explosions, this galaxy offers an ideal environment for studying how these enrichment cycles unfold across space and time. Detailed maps of abundance ratios like O/Fe and C/S reveal that chemical feedback is often localized, shaped by the type of progenitor and the dynamics of the receiving medium. Some zones retain stratified elemental layers, others show turbulent mixing likely driven by shear flows and convective instabilities. These variations serve as calibration points for galactic chemical evolution models, shedding light on the formation of metallicity gradients and the temporal evolution of the interstellar composition. Dust grains, formed in AGB stars and supernova remnants, add further richness to the chemical story. These particles are not mere bystanders, they shape the thermal physics and chemistry of molecular clouds, regulate star formation via shielding, and act as surfaces for complex molecule formation. Over time, grains are modified by radiation, shocks, and grain-grain interactions, altering their size distribution and composition. In this galaxy, observations of silicate absorption near 9.7 micrometers and polycyclic aromatic hydrocarbon, PAH, emissions around 8 to 12 micrometers show regional variation that traces both environmental conditions and the life cycles of dust itself. PAHs, for instance, flourish in quiet interarm regions but are destroyed near OB clusters, illustrating a delicate balance between dust survival and stellar radiation. Another emerging frontier lies in the galaxy's vertical structure. Faint H-alpha emission reveals a warm, diffuse ionized gas layer, an extraplanar component that rises several kiloparsecs above the galactic midplane. Supported by turbulent and thermal pressure, this EDIG halo may be driven by supernova-powered superbubbles or galactic fountain flows, gradually building up a chemically enriched halo. Such a structure resembles the circumgalactic medium seen in larger systems and may represent its early phase, already influencing the galaxy's baryon cycle. Cosmic rays also play an increasingly recognized role in sculpting this vertical environment. Relativistic electrons accelerated by supernova shocks escape into the halo, where they trace out large-scale magnetic loops and contribute to synchrotron emission detected at radio frequencies. Vertical gradients in radio continuum brightness suggest that these particles diffuse and advect over kiloparsec scale distances. The resulting winds, though weak compared to those in starburst galaxies, may be sufficient to lift both gas and magnetic fields into the halo, enriching the surrounding medium and sustaining low-level outflows. Even in the absence of an active galactic nucleus, taken as a whole, this luminous spiral stands as a vivid example of how galaxies are not static star catalogs or gas reservoirs, but dynamic, self-regulating engines of cosmic change. Its arms are not just architectural flourishes, but gravitational wavefronts sweeping through the disk, sculpting matter, igniting starbursts, and imprinting enduring patterns of chemistry, radiation, and magnetism long after the light of young stars fades. Its nucleus, far from inert, is a site of subtle flows, hidden mass, and enriched complexity. And its surrounding halo, often assumed empty, is in fact a quiet archive, accumulating light, metals, and memory through outflows and fountains. To observe such a galaxy is to read an unfinished manuscript of cosmic evolution, each supernova a punctuation mark, each filament of gas a narrative thread, each photon a whisper from the past. Its stellar population encodes its origins, its gas and dust trace its present processes, and its spiral choreography hints at a future written in feedback, entropy, and gravitational order. Its role as a cosmic archetype even extends into the high-energy domain. Beyond the visible and infrared glow, this system produces a faint yet meaningful background of X-ray emission, traced to the aftermath of powerful events and compact stellar remnants. Observations from telescopes like Chandra and XMM Newton have uncovered dozens of point sources embedded within its disk, many identified as high-mass X-ray binaries, systems where neutron stars or black holes feed on the winds of massive companions. These luminous pairs are direct legacies of recent star formation and act as cosmic chronometers, their presence marking the time since massive stars first ignited. The luminosity function of these X-ray sources follows a characteristic power law seen in other star-forming systems, suggesting the presence of universal accretion physics across galaxies. Some of the brightest sources may be ultraluminous X-ray emitters, ULXs, enigmatic objects whose output surpasses the Eddington limit for stellar mass black holes. These may harbor intermediate mass black holes or manifest extreme accretion geometries with beaming or disk instabilities. This galaxy's X-ray population provides a window into such exotic regimes, linking compact object evolution to stellar feedback and metallicity. Even at gamma-ray energies, though currently below detection thresholds, theoretical models predict emissions from cosmic ray interactions within the interstellar medium. Collisions between relativistic protons and ambient gas create neutral pions, which decay into gamma photons. While current instruments lack the sensitivity to fully resolve this emission from the fireworks galaxy, Future observatories such as the Cherenkov Telescope Array, CTA, may probe these processes directly, offering insight into how ordinary spiral galaxies like this one accelerate and confine cosmic rays over millions of years. One of the most compelling frontiers now emerging is the relationship between the galaxy's magnetic architecture and its dynamo history. Theories of galactic magnetic field generation suggest that strong turbulence and rapid rotation in young galaxies drive field amplification through a turbulent dynamo. Over time, these chaotic fields coalesce into coherent, large-scale structures. With its mix of ordered magnetism and active turbulence, this system may occupy a transitional state in that evolutionary path. Using Faraday tomography, where polarized radio waves reveal magnetic field geometry through frequency-dependent rotation, astronomers can now reconstruct the three-dimensional magnetic topography of its disk. These maps unveil the pitch angles, reversals, and helicities of field lines, directly comparing real data to the predictions of galactic dynamo theory. Its structure reveals tight spiral arms with pinkish hydrogen emission regions, H2 zones, glowing from ultraviolet radiation emitted by newborn stars. These stellar nurseries are teeming with protostars, each a pocket of cosmic creation. Dust lanes, visible in infrared, weave through the galactic disk like shadowed brushstrokes on a canvas. When viewed across the electromagnetic spectrum, from radio to X-rays, this system emerges as a chaotic yet harmonious symphony of gas flows, magnetic fields, and stellar winds. At its core lies a site of intense star formation, emitting powerfully in the far infrared, heated by ultraviolet light absorbed by interstellar dust. Unlike grand design spirals with defined bulges or bars, this central region is soft, turbulent, and asymmetric, perhaps the consequence of past mergers or gravitational interactions with smaller companions now dissolved into its halo. Observations have revealed strong magnetic fields, threading through the arms and amplified by a galactic dynamo effect. These fields not only shape gas motion but influence cosmic ray propagation, adding depth to the galaxy's already dynamic nature. Despite its activity, this spiral remains relatively isolated, part of a sparse group within the M101 filament. Its seclusion, paired with a vast cold gas reservoir, may help explain its high star formation rate. Each supernova does more than expel heavy elements, it triggers the next wave of stellar birth, creating a heartbeat of death and rebirth echoing across thousands of light-years. This galaxy serves as a cosmic lab for understanding stellar death and chemical enrichment. With a record number of Type II supernovae, astronomers have traced their progenitors, observed fading afterglows, and tested core collapse models. Spectroscopy reveals metallicity gradients in its arms, higher near the center, indicating long-term enrichment and radial mixing. Molecular gas traced by CO emissions appears in vast, turbulent clouds that give rise to stars through gravitational collapse. X-ray and ultraviolet observations expose hot, diffuse plasma surrounding recent supernova activity. These regions mark the boundaries between gas phases, some condensing into stars, others suspended in ionized states by stellar winds and radiation. Radio polarization maps reveal a well-structured magnetic field, not only guiding cosmic rays but potentially regulating star formation and stabilizing interstellar clouds. The galaxy's rotation curve further implicates the presence of dark matter. Discrepancies between visible mass and orbital speed suggest a dominant halo, especially beyond the optical disk. Mass models favor a chord profile, potentially sculpted by baryonic feedback. Observations of warps, HI asymmetries, and faint stellar streams point to past minor mergers and continued gas accretion, likely feeding the galaxy's inner regions and maintaining its vitality. The galaxy's flocculent arms, unlike the grand spirals of M51, are likely maintained by internal dynamics, swing amplification, feedback loops, and turbulence, rather than density waves. These arms form, dissolve, and reform in transient rhythms, illustrating a self-order rich in molecular gas and relatively free from external disturbance. Beyond the visible disk, extraplanar H-alpha emission suggests the presence of a warm, diffuse ionized gas. Superbubble blowouts and galactic fountains lift enriched gas into this extended region, slowly building a chemically rich circumgalactic medium. Relativistic particles traced by synchrotron radiation extend several kiloparsecs above the disk, suggesting that even without a central AGN, the galaxy produces mild winds that lift gas, dust, and magnetic fields into the halo. In the infrared, dust heated by massive stars glows brightly. Spitzer and Herschel observations place this system near the threshold of luminous infrared galaxies, LIRGs. Its spectral energy distribution reveals multiple dust temperatures and compositions, shaped by sputtering, radiation, and grain collisions. Dust not only reprocesses starlight but also acts as a catalyst for molecular chemistry and star formation. Dust is further shaped by local conditions. PAHs and silicate features vary across the disk, strong in interarm regions, destroyed in intense star-forming zones. This interplay between radiation and dust grain evolution offers a microphysical view into how galaxies recycle matter and light. The nuclear region may harbor a low-mass black hole hidden within a nuclear star cluster. Velocity dispersion peaks and faint infrared signals hint at such a presence, placing it on the low end of the black hole bulge-mass relation. If confirmed, this compact object adds another piece to the puzzle of black hole formation in late types. Radial migration, where stars shift outward or inward without significantly altering their orbits, helps explain how the outer disk can host older stars that originally formed near the core. This redistribution complicates efforts to trace chemical evolution but also contributes to the formation of thick disks and extended UV structures. The Fireworks galaxy is also a rich time-domain laboratory. Supernovae like SN 2004 ET and SN 2017 E have been observed across the electromagnetic spectrum, providing insight into explosion dynamics, nucleosynthesis, and dust formation. Light echoes reflected from surrounding dust even enable 3D reconstructions of the interstellar environment. High-energy emissions from X-ray binaries further trace recent star formation. Some sources may be ULXs, candidates for intermediate-mass black holes or exotic accretion states. Gamma-ray emissions from cosmic ray interactions remain undetected but may become visible with future observatories like the CTA. The galaxy's magnetic fields, both ordered and random, play an invisible but essential role. They align with spiral arms, thread through interarm space, and may help maintain arm structure in tandem with gravity and turbulence. Polarized far-infrared emission reveals their interaction with aligned dust grains, observable by missions like SOFIA and future JWST successors. Such magnetic fields are not isolated phenomena. They are woven into the ISM itself, shaping accretion flows, collimating outflows, and influencing the spatial coherence of the disk. Faraday tomography techniques are beginning to map their 3D geometry, offering insight into pitch angles, helicity, and the operation of large-scale dynamo processes. Simulations now the galaxy's observed properties, morphology, metallicity, and regulated star formation, by including magnetic feedback and cosmic rays. These models suggest that the Fireworks galaxy exemplifies an equilibrium point in galactic evolution. Feedback maintains order, accretion sustains growth, and internal processes shape structure. Looking forward, its evolution may follow a familiar arc. If star formation continues at current rates, it will eventually consume its molecular gas. Yet, signs of outer disk accretion suggest that quiescence is still far off. Over billions of years, it may transition into a more lenticular form, spiral arms fading, supernovae waning, and stellar populations aging into red stillness. But its chemical fingerprints, stratified halo, and magnetic spirals will remain, fossil records of a more active past. In this way, the fireworks galaxy embodies the life cycle of galactic systems. It is not static, not passive, but alive with formation, feedback, and transformation. Its spiral arms are currents of gravitational choreography, its supernovae, punctuation in a cosmic manuscript. It is a galaxy in motion, threaded with invisible forces and radiant with stories written in light and time. Every wavelength we observe adds another page: cold gas poised to collapse, warm dust glowing from stellar birth, hot plasma rushing through blown-out cavities, and ancient stars whispering of epochs gone. This is no simple object, it is a galactic chronicle, unfolding across millions of years. As our instruments sharpen and theories deepen, this nearby spiral continues to reveal new layers of meaning. It stands as a luminous bridge between what we can resolve and what we only imagine. And in the silence of space, it speaks in a language of energy and order, a language we are just beginning to understand. To gaze upon this galaxy is to look into the past, and into the very mechanisms that shape the future of galaxies like our own. It reminds us that the universe is not still, not quiet, but alive with motion. And in that motion, we of the cosmos, subtle, relentless, and beautiful.
When discussing the strength of galaxies like the Andromeda and Milky Way, it's not about a destructive head-to-head battle in the conventional sense, but rather a comparison of their gravitational influence, mass, and overall stellar content. These cosmic giants are on a long, slow dance, gravitationally bound within our local group, and their interaction is dictated by the fundamental forces of the universe. For a long time, the Andromeda galaxy, M31, was widely considered the more massive and larger of the two. With an estimated diameter of about 220,000 light-years and containing roughly 1 trillion stars, it certainly appears more expansive than the Milky Way's approximately 100,000 light-year diameter and 200 to 400 billion stars. This numerical advantage in stars often led to the assumption that Andromeda held a dominant gravitational sway. However, recent, more precise measurements, particularly concerning the distribution of dark matter, the mysterious, invisible substance that makes up the majority of a galaxy's mass, to shift this understanding. Some studies suggest that while Andromeda might indeed boast a greater number of stars and a larger physical diameter, the Milky Way could actually be more massive when considering the full extent of its dark matter halo. One study, in particular, indicated that the Milky Way might be almost twice as massive as Andromeda due to its dark matter content. Dark matter, despite being undetectable directly, exerts a significant gravitational pull, influencing the motion of visible matter within and around galaxies. Therefore, a galaxy with a larger dark matter halo, a stronger gravitational influence. The concept of strength is purely gravitational. The galaxy with more mass, whether in the form of visible stars and gas or invisible dark matter, will exert a greater gravitational pull on its surroundings. This pull dictates the orbits of satellite galaxies, the dynamics of intergalactic gas, and ultimately the trajectory of other major galaxies within a group. The infamous predicted collision between the Andromeda and Milky, once thought to be an inevitable head-on impact in about 4.5 billion years, is a testament to this gravitational interaction. While new research, incorporating more variables and uncertainties in galactic motions, suggests that the probability of a direct collision might be closer to 50-50 within the next 10 billion years, a close encounter leading to a remains a significant possibility. Even if they don't directly collide in the initial pass, their mutual gravitational attraction will likely lead to repeated close approaches, gradually drawing them into a larger, new elliptical galaxy, affectionately dubbed Milkomeda. This galactic dance is a slow-motion ballet where the immense gravitational forces are the unseen choreographers. The stronger galaxy, in terms of total mass, will ultimately play a more dominant role in shaping the merged entity, drawing in and disrupting the less massive components of its partner. However, it's important to remember that these are not violent, destructive events for stars. The vast distances between stars mean that stellar collisions are extremely rare. Instead, the galaxies interpenetrate, their stars settling into new orbits around a common center, while gas and dust clouds can trigger bursts of new star formation. Adding another layer of complexity to this gravitational dance are the numerous satellite galaxies that orbit both Andromeda and the Milky Way. Each of these smaller galaxies, though far less massive, contributes to the overall gravitational potential of its host, influencing the trajectories and ultimate fate of the larger spirals. Recent simulations have even incorporated the gravitational influence of the Milky Way's own largest satellite, the Large Magellanic Cloud, LMC, which, despite its relatively small mass, around 15% of the mass, thought to exert enough sideways tug on the Milky Way to potentially alter its course and reduce the chances of a direct collision with Andromeda. This highlights how minor gravitational perturbations can have significant long-term consequences in the vast cosmic arena. The precise mass estimates of both galaxies are still subject to refinement as observational techniques and theoretical models improve. Measuring the total mass of a galaxy, especially the elusive dark matter component, is inherently challenging. Astronomers rely on indirect methods, such as observing the rotational speeds of stars and gas within a galaxy, or the motions of its satellite galaxies, to infer the distribution of mass. Discrepancies between different studies often arise from variations in these methods, the data sets used, and the underlying assumptions in the models. Ultimately, the question of who is a dynamic one, reflecting the evolving understanding of our cosmic neighborhood. While Andromeda was long considered the heavyweight, the Milky Way's significant dark matter halo suggests it might be a more formidable gravitational entity than previously thought. Regardless of which galaxy holds the slight edge in total mass, their interaction is a testament to the immense power of gravity on galactic scales. The future Milkomeda galaxy will be a grand testament to this ongoing cosmic ballet, a spectacular result of the gravitational dialogue between two of the local group's dominant members. The details of their merger, whether a direct impact or a prolonged series of close encounters leading to a final embrace, to be a fascinating area of research, revealing more about the life of galaxies across the universe. To delve deeper into the scientific comparison of Andromeda and the Milky Way strength, we must consider not just their visible components, but also the enigmatic dark matter halos that envelop them. The very definition of a galaxy's gravitational influence is inextricably linked to the extent and density of its dark matter distribution. Astronomers model these dark matter halos using various theoretical profiles, such as the Navarro-Frank-White profile or the Einasto profile, which attempt to describe how the density of dark matter changes with distance from the galactic center. By fitting these models to observational data, primarily the rotation curves of stars and gas within the galaxies and the kinematics of their satellite galaxies, researchers can infer the total mass of the dark matter halo. The rotation curve, a plot of orbital velocity versus distance from the galactic center, remains relatively flat far beyond the visible disk of a spiral galaxy, a strong indication that invisible mass, dark matter, continues to exert a significant gravitational pull. Early estimates often favored Andromeda as more massive, primarily due to its larger stellar disk and higher estimated star count. Its disk is significantly wider than the Milky Way's, and it hosts a more populated globular cluster system, which can serve as a proxy for the overall galactic environment. However, the true picture becomes more nuanced when considering the entire virialized volume of the galaxy, the region where its gravitational influence dominates over the Hubble flow, the expansion of the universe. This is where the dark matter halo plays a crucial role. Recent breakthroughs in precision astronomy, particularly with data from missions like the Gaia Space Telescope, have provided unprecedented accuracy in measuring the proper motions, sideways movements across the sky, of stars, and, crucially, satellite galaxies. These measurements, combined with radial velocities, movements towards or away from us, allow precise reconstruction of galactic orbits and, consequently, more refined mass estimates. Some of the latest research, incorporating these advanced datasets and more sophisticated n-body simulations, which model the gravitational interactions of thousands or millions of particles representing stars, gas, and dark matter, suggests a tantalizing possibility. The Milky Way might indeed possess a more massive dark matter halo than Andromeda. While Andromeda might have more stars and a larger luminous extent, the Milky Way's dark matter halo could be denser or extend further, giving it a greater overall gravitational pull. This revised understanding has profound implications for the predicted collision between the two galaxies. The LMC's gravitational tug on the Milky Way, as mentioned earlier, is a key factor. If the Milky Way's dark matter is more massive, the LMC, as a satellite of the Milky Way, would also exert a relative influence, potentially nudging our galaxy off its previously predicted Andromeda. The precise vector of this tug, influenced by the LMC's own orbital parameters, becomes a critical variable in the simulations. The ongoing refinement of these galactic mass estimates and orbital parameters underscores the dynamic nature of astrophysical research. It's a continuous process of observation, hypothesis, modeling, and further observation. The local group, serves as a natural laboratory for studying galaxy formation and evolution. By analyzing the intricate gravitational dance of its members, including the dominant Andromeda and Milky Way, astronomers gain vital insights into the distribution of dark matter, the history of galactic mergers, and the ultimate fate of cosmic structures on grand scales. The strength of a galaxy, therefore, is not a static quantity, but a complex interplay of its visible and invisible components, perpetually refined by the relentless pursuit of scientific understanding. Continuing our scientific exploration of the Andromeda-Milky Way rivalry, the concept of viral mass becomes paramount. This isn't just about the stars we see, but the entire gravitational sphere of influence. A galaxy's viral mass includes not only its luminous matter, stars, gas, dust, but also its dominant dark matter halo, extending far beyond the visible disk. The boundary of this viral radius is where the galaxy's gravitational pull balances out the expansion of the universe. Estimates of these viral masses are derived from complex observational data, particularly the kinematics of satellite galaxies orbiting the main spiral. The velocities of these smaller galaxies are direct tracers of the gravitational potential well of their host, allowing astronomers to weigh the invisible dark matter. One of the most powerful tools for understanding galactic masses, and thus their strength, is the study of gravitational lensing. This phenomenon occurs when the mass of a foreground galaxy, or cluster of galaxies, bends the light from a more distant background object, distorting its image. The degree of bending directly correlates with the amount of mass, including dark matter, in the lensing galaxy. While strong lensing is more common with massive galaxy clusters, weaker forms of lensing can be detected around individual galaxies like Andromeda and the Milky Way, providing independent constraints on their dark matter distributions. Furthermore, the cosmic web, the large-scale structure of the universe, composed of filaments, voids, and matter, also plays a subtle but significant role. Galaxies don't exist in isolation. They are embedded within this web. The gravitational tides exerted by surrounding large-scale structures can influence the accretion of dark matter onto a galaxy and even its overall morphology. For instance, the Milky Way and Andromeda are both falling towards the Virgo cluster, the nearest large galaxy cluster, at hundreds of kilometers per second. This larger-scale gravitational pull within the local group and beyond subtly affects their individual trajectories and, over cosmic timescales, could play a role in their merger. Beyond just mass, the strength of a galaxy can also be interpreted through its star formation rate, SFR, and its evolutionary stage. The Milky Way, while perhaps having a denser dark